Okay, let us continue our review of the year, and we're going to learn some new stuff today. We're going to review things that we've already talked about, but we're going to do questions 17 through 32, of which, of course, will be tested on tomorrow. Okay, so jumping in, number 17 is a volume stoichiometry problem. And the thing with volume is it's going to be 22.4 liters on one side and 22.4 liters on the other side. So we kind of look at these problems a little bit differently. So no matter what gas it is, the volumes will be identical at the given conditions. So we're going to use LR, or limiting reactant, with a volume stoichiometry problem. So go ahead and write this hypothetical chemical reaction. And the real key to getting these problems is recognizing that 2 to 1 to 2 to 4 ratio. Okay? Now, what makes number 17 kind of tricky is that they give you two starting amounts, okay? And then they say how much of this will be produced, all right? So I want you to think about that a little bit, of if you're looking at this, if I have 18 liters of the 2A and 12 liters of the B, how much D would I get? Well, the answer is, hopefully some of you got this right, would be 18 liters. And the reason is this would be 2 parts to 1 part to 2 part, so it's going to be the same as the amount of A, because that's how gases behave. It doesn't matter what they are, providing you didn't run out of B. And if we look at this, half of 18 would be 9. So if you wanted to look at how much of B was left over, let's say that was the question. Well, 9 would get used up because 18, half of that would be 9, meaning the leftover would be 3 liters left over. Okay? So think about that, in terms of these ratios. This is excess, this is your limiting reactant right there, which of course then will determine how much of the D you get. And using that same line of thinking, here's a challenge. What would 4E be? So you've got 2A and 2D are your best ones to use to figure that out, and the answer would be 36 liters, because it would be twice as much because of the ratio of the moles there. Okay, so not an easy question to start out on, but it is something that if you really think about those coefficients, I think that one will go pretty well. And I'm going to continue with my giraffe theme and just pictures of giraffes and funny things about giraffes. I thought this was kind of funny because the little privacy walls, because they're tall. Giraffes at the urinal. All right, now we're going to talk about energy and thermodynamics. This is something, one of those things we don't quite have time to get to, and honestly, we usually kind of leave that more for physics. But I do like to introduce some key concepts. So hit the pause and get this all written down, and then I'm going to explain it. Pause. All right, welcome back. You got this beautiful diagram right now. Maybe you even color-coded it like we did here, where you have reactants up here, products up here, and this is energy, this axis. This one's just kind of as the reaction proceeds on the x-axis. So as you go from reactants to products, you have to climb a hill of energy. That's why the logs that you have stacked up to put in your fireplace don't just start on fire. You got to kind of spark them a little bit to get that reaction going, and then once you do, you get all that heat will be given off as the products go down to the lower energy right there. So you can see we call this delta H, which means change in H. You can think of that as being heat. The fancy name for that is enthalpy. All right? And the fancy name for the hill that you have to climb is the activation energy. A couple of other things. This is an exothermic reaction. These are at high energy. These are at low energy. Where does that energy go? It comes out. So it feels hot to the touch. And anytime delta H is negative, because you go downhill, then it is an exothermic reaction. All of those things will help you. And you need one more concept for this question, which is you can lower the activation energy of a reaction. You can make it happen faster and easier, and that is by adding a catalyst. Okay? So if you add a catalyst, that activation energy will lower. So we'll put the catalyst part in red, the regular activation energy in blue, and you just get a lower activation energy if a catalyst is added to a reaction. All right? So get some good notes about that, and you'll do well on this one. I just like this one because it was a giraffe wearing pants. I don't think it's anything funny about it other than that. And it has my name, Jeff the Giraffe. All right. So here's an example of a chemical reaction that uses a fraction to balance it. So go ahead and write this down as an example. And the reason they do that is so that you can get 1 mole of product. That happens sometimes. And then the delta H is negative 98.23 kilocalories per mole. So we're still talking about thermodynamics. You do know one thing. If delta H is negative, it is, you guessed it, exothermic. Okay? So here's the problem that is very similar to what number 19 was going to be. It says, how many kilocalories of energy are given off when 235 grams of product is formed? All right? So the problem with, you can use trust the factor label method, trust dimensional analysis to get you there. When you look at these two things here, all right, you got two numbers. This one, if you look at it, is actually a conversion. There's this many kilocalories per mole. This is just a singular unit. So, because of that, we'll start this problem out by writing 235 grams. And then you know that grams is going to go on the bottom. The 58.5, of course, that I got was, this is the product. So I took chlorine 35.5, sodium 23.0, and you add them up. Circle square method, and that gives you, you have now converted grams into moles. And I now, from this conversion, I know that there are 98.23 kilocalories per 1 mole. You don't have to use a negative symbol because they said, you know, are given off, and that's what exothermic means, is the energy is given off. You multiply the top numbers, divide by the bottom numbers, you get 395 kilocalories. This example will prove very useful for you in doing number 19. And if you can just follow the same logic, then you're going to be in great shape. All right. Another giraffe joke there for you. Okay, now question number 20 is kind of saying, did you watch the videos from Tuesday after we finished the first part? I said watch these 2 videos, get an idea what equilibrium is, that it goes back and forth, where they had the arms and then the arm coming out of the nose. Kind of a funny little example of that. But this, if you have a reaction like this, A moles of A plus B moles of B give you D moles of D plus E moles of E. Now you practiced several of those problems. Hopefully you already have this in your notes. And now you can write on those part of your notes that this is number 20. Remember, for writing the KEQ expression, the products go on the top, and you put square brackets, and the little coefficient here becomes an exponent. So that's E moles. And I didn't put D because liquids are left out, because you don't talk about concentration of a pure liquid. That would be saying like, ooh, that water is really dilute. What? Ooh, that's strong water. Somebody made a strong water. No, it's not a solution. These are pure liquids. So you leave those out, as is the case with solids. So the reactants, first 2 things here go on the bottom, but you're leaving the solid out. B mole risen to the B power. Now you did some actual examples with formulas last time, and if you haven't watched that video, I would actually go back and do that right now and put those examples right here under question number 20. Okay, just remember, products on the top, reactants on the bottom, solids equal 1, liquids equal 1, and the brackets mean concentration, and that is in molarity, which we are actually going to review that coming up in the future on preparing for this test. But it's a way of talking about concentration in moles per liter, capital M. So that's what the units are for those things. So that'll get you through number 20. For number 21 and 22, make a note to yourself to get your reference packet ready. Okay? As a matter of fact, I'm just going to go grab mine. So I've got my reference packet here, and inside there's kind of this orangey, pink, salmon colored sheet that has all kinds of notes about the periodic table, both front and back. That stuff will be very helpful to you, and you can just say that for questions 21 and 22. We're going to be making reference to that. All right. So just remember, how things are grouped up. Just a nice review of the periodic table. The 2-corner philosophy was a really good conclusion that we reached. Remember, we had this corner tend to be really small and very electronegative elements. These are really big. They don't want anything to do with electrons. So those trends of having those 2 corners on the periodic table, something as a hint, and that's on those on the reference sheets, the size and trends and all that. Okay, number 23. I'm just going to classify this as a thinker. All right, there's the thinker statue. You know what he was actually thinking? So what's he got that I have? All right. So number 23, let's review our definition of the mole. That will be useful. And that there are that many grams of carbon-12 in 1 mole. And it's just going to be a thinker about this. The whole system's based on carbon having a mass of 12. What if they didn't? What if they said carbon had a different mass? And you're really going to have to put some thought into that one. Okay? So we'll stop here and go on to the next video.